Welcome everybody, Mr. Allen here. I'm going to quickly go through what we've seen so far when dealing with graphing and polynomials, specifically in the Desmos activities. This is just kind of an overview of some of the terminology that we'll run into in the next little bit, and what we should have picked up throughout the course of the Desmos activities if we were sort of getting everything out of it that we could. So we'll start just looking at a basic parabola here. The keys, obviously, we hopefully established by now the roots of the equation, sort of where the zeros are. I can see that I'm going to have a 0 at -5 here, or -5. I'm going to have a 0 at 3, because again, those values, when plugged into this equation, will give me a calculation of 0. Put a 3 in here and a 3 in here, and I end up with 0 times 8, 0, obviously, for my y value. Similarly, if we put the -5 in, I get -8 here and 0 here, 0 again. The value out front, the a value here, just stretches my graph. As the a value gets higher, I'm essentially saying I'm going to take whatever calculation I would have had already and multiply it by the number out front. So the y value gets faster, or it gets larger by 5 times here, 5 times, or 6 times, or whatever. If that a value is negative, again, pretty obvious, I think. We have a calculation for y. We're multiplying that value by negative whatever. Any positive values will become negative. Any negative values will become positive. If I think about this equation in expanded form, my highest power will be an exponent of 2. And the thing to note there is my graph has two directions that it can travel. Regardless of my a value, I will always have my graph going 1, 2 directions. So just as far as terminology goes, degree of our function is the highest exponent in standard form. So if we look at the blue equation here, my x cubed is my highest power. And so that's a degree 3 or a third degree or a cubic function. My green equation here, if I did multiply this out, I would end up with -3x cubed, times x squared, so -3x to the 5th, along with, of course, a bunch of other terms. But the important one is that the highest power will be a 5, so I'll have a degree 5 or a 5th degree, or what we call a quintic function. I'll come back here in a second. Now, as I add zeros to this equation, you can see that when I had just the 2 zeros, I had 2 directions. Essentially, though, when I had a second degree function, I had 2 directions. Here with a third degree function, again, if I multiply this out, I get an x cubed term times whatever my a value out front is. I end up with my graph going basically up to 3 directions. If I look at the basic x cubed curve for a moment, my graph even here is going up and then kind of flattening out for just a moment and then going up again. So it still has that same 3 directions. So once again, regardless of what my a value is out front, I can see that my graph is basically going 3 directions. Again, it's really up to 3 directions, depending on what else is going on. But I have that same idea that my x cubed has 3 directions to it. If I continue that pattern, we will see a 4th root, 4 zeros, 1, 2, 3, 4, and my graph goes 4 directions. And once again, negative out front just flips it over, but you can start to see we always have that 4 directions. Okay, so the last thing here establishes the degree of the polynomial, establishes the maximum number of directions it will travel, or it can travel. And note, the term turning points talks about how many times does the graph actually turn. I often get that question. It's a common phrase in a lot of math textbooks in particular. Instead of talking about the number of directions the graph travels, they talk about the number of turning points on the graph. It's always going to be 1 fewer, because of course if my graph is going to go 4 directions, it has to turn 3 times. The turning points end up being these maximum minimum points. So once again, just another way to say the exact same thing. A turning point would be the number of times it hits up a maximum or minimum and then literally turns, the graph goes in a new direction. We saw this quickly just in kind of playing there. The sign of the leading coefficient is the number in front of the highest power of x, or my degree term. And so here, if I did multiply this out, you can probably see that I would end up with a positive 14 out front. My graph is going to be a regular cubic function like all the ones we just saw. In the second case, if I did multiply this out, I would end up with a negative 3, again, x to the 5th. Because of the negative out front, my graph would flip vertically. And again, that's exactly what we saw when we were playing with the a value on the slider. A couple more things here, roots, zeros, and x-intercepts. All those terms mean the same thing for us. And then as we go through here, I'll shorten this so we can see it better. Now, if I were to have an exponent on one of my roots, this is called an order 2 root or a double root. And what you can see is that at that location now, my graph takes on, to some extent, the shape of a parabola. That part of my graph, if that were my whole graph, would be a parabola with a 0 at -5. So the blue graph is going to take on the characteristics of the parabola at that location. Similarly, if we were to change this to a cube here, my graph would have the basic shape of a cubic function at that -5 now instead. And so if I can zoom out a little bit, my graph now is a 5th power, because again, x cubed times x, so I'm going to have 5 powers. I've got my 1 direction, 2, 3, 4, and 5 directions with those same 3 roots. Again, because I'm cubic at that -5. So order n roots basically just means there's an exponent on the individual root, and again, the graph takes on the shape of the basic curve at each of those roots. Here at x equals 4, there will be a parabolic shape. Here at x equals 8, there'll be kind of a cubic shape. Now last term, n behaviors, sometimes a problem. N behaviors are exactly what they suggest. They're asking you what happens on the ends of the graph, on the left side of the graph and on the right side of the graph. Well, what we've seen is no matter what I've drawn here, my graph has always either started at the bottom over here on the left and then kind of come up, done some ups and downs and finished up or finished down, or started at the up on the left and kind of, again, done something, finished up or finished down. So these 4 arrows are basically the options. My graph will always be headed up as it goes left, or down as it goes left, up as it goes right, or down as it goes right. And the way we typically write that is using this sort of notation. This is suggesting that y is, the arrow says, heading towards or approaching infinity. Down here, y is approaching negative infinity. Similarly, x approaching negative infinity means the graph is going to the left, or as we're going to the left, and the x approaching positive infinity means as we're going to the right. So as far as describing n behaviors goes, you could put something as simple as a sentence saying, on the left side of the graph goes up. On the right side, the graph goes down. You could put something saying the graph goes from the second quadrant, so the upper left quadrant, to the first quadrant. So it starts up in the second quadrant and does whatever and finishes in the first quadrant. Our quadrants, in case you've forgotten, 1, 2, 3, and 4. So something along those lines would work as well. But just for our purposes, n behaviors, that's all it's asking. What is happening on each side of the graph? So hopefully that helps summarize what we've seen and get you going on the follow-up work.